So, let's talk about, from my point of view, a bit more advanced things. So in the first part, I want to talk about loop scheduling, some of the things we already mentioned yesterday and 2 days ago about collapsing loops and how to partition our loops into the thread blocks and threads and so on. I will go in that in more detail. And then afterwards, if we have enough time, if I do not spend out the first session too long, I would just show you really quickly how to do it with, in CUDA we call it streams, so we do dependent tasks, then we can asynchronously schedule our tasks and do maybe also overlap them in a nice way. So I also have a short reminder at the beginning. We already did yesterday in the second exercise session using optimized libraries like BLAS, LAPACK, ScalaPack. So just as a reminder, so in the libsci Excel, so from Cray, we already provide these libraries. You just have to load the libsci SL module, and then in the intro libsci SL there is a huge documentation you can read for that. But there are also other libraries. I think yesterday in your example was cuBLAS, right? If I remember correctly. Yeah. So cuBLAS, and there's also Magma and Q, FFT, and a lot of others. How to use them, we saw yesterday just on the slides as a reminder. So in OpenMP, you use these use device pointer in your target region before the library call, and in OpenACC it's similar, you just use the use device directive. That's short, fast. Now to come to the next point, so after you introduced your kernel, you optimized your data movements, what we did yesterday. For this you have to understand, we want to also now optimize the scheduling of the kernel, and therefore we need to understand how the hardware works. And I mean, Vasilos already gave an overview how the hardware looks like. That is just as a short reminder to bring that back in mind. So as the first point, we have to keep in mind that we need a large number of parallel tasks. We want to distribute these, as we already saw, a huge amount of parallel threads we can create on these. Pascal has 3,800 something cores, right? 3,500, okay. So quite a lot. And with CUDA, which is usually the underlying structure, it handles that in a certain structure. So we already mentioned that there is a grid of thread blocks in CUDA, and every thread block has a certain number of threads. But there are also so-called warps. So 32 of these threads are processed in a SIMD version. So 32 threads do work in lockstep, so all do the same instructions but on different data. So if we have some kind of branches distinguishing our data, one part has to be done certain calculation and another part has to be done another calculation. In an optimal way, at least always portion of 32 data elements work on the same instruction, or the same instruction work on the 32 data elements. Because if we have smaller portions, then we work in the SIMD part, but then we do multiple steps with masking out different portion of our data. So then we increase our the amount of instructions for doing more or less the same thing. So this is quite crucial. This is important to keep in mind. And in OpenMP, it's a bit, I mean, okay. In OpenMP, we have similar things. So we also generate a kind called league of threads, which maps quite nice to these CUDA thread blocks. And within these thread teams, we have a certain amount of threads. And again, we work in these SIMD instructions mapping to the CUDA warps. So this distribution we do with the teams statements and then distributing to the different threads within these teams we do with the distribute statements. In OpenACC, it is kind of similar. There we have the parallel statement as we used yesterday. But then we can also distinguish, I mean, there are two ways how to do it. We can just do with the parallel statement and then distribute within these threads, but we have also the possibility to use these three levels of parallelization, so within gangs, workers, and vectors, as Marcus already mentioned. So the gangs then map to these CUDA thread block, the workers maps to these warps, so to these 32 elements of 32 threads, and the vector is then the threads within this warp. Yes?
From the second point, I don't understand the last 2 points. So if a worker maps exactly onto a CUDA warp, and a vector is a set of 32 threads making up a warp, what is the difference between a vector and a worker?
So, okay, let me go one step back. You have these thread blocks, which is then kind of distributed into certain warps. Warps consist of 32 threads in that sense. So you have a certain amount of warps within there, and within the warp you have 32 threads. And with these three clauses, you distribute to these three levels of parallelization. So in the gang clause, you parallelize within to the thread blocks. With the worker clause, you parallelize to the warps. And with the vector clause, you parallelize within one warp. Okay?
Just a quick, an additional thing. This is also related to the compiler. So it's, I think, for the PGI, worker is equivalent for vector, right? The clause. Or just
no, they are not equivalent.
Okay. Okay, then probably in older version. I don't remember.
Sizes and things are different between two compilers, but there's not an equivalent between worker and vector.
Okay. Okay.
But your point is also right. I mean, the standard defining the whole thing is a bit how to say that? Not explicit. So each vendor, each compiler can implement it in its own way and could vary from compiler to compiler. In that sense, it's, as we already mentioned, it's always useful to see the compiler feedback, what is really done within the compile time. Yeah, as mentioned, if you have your loop nest, so your nested loops, these are then divided to the thread blocks, and there are different possibilities how that will be done. So I will just skip that. Then there's kind of a summarized slide, which I already mentioned. So the teams distribute about the thread teams that distribute directive partitions within these thread teams. So this is the CCE behavior, and you can also use the SIMD directives to tune then the scheduling within the team. For OpenACC, it looks similar. We already mentioned that you have the parallel directive for the gangs of worker and vector behavior, and the loop directives for partitioning within that. And as Marcus already shown, you can use these gang, worker, and vector clauses to really specify yourself how you want to distribute your huge amount of tasks to the different levels of parallelization. So maybe to go in more detail why these warps really matter. So I mentioned that these are really slots of 32 wide slots of a vector, and this is, I would say, you can really imagine this as vectorization on a CPU. So you really need independent data which the same operation should act on. And the compiler also needs that to really optimize that. So okay, I just want to mention here that, okay, we can then optimize our operation with this vectorization, but in the first point, we need to think of the data movement, since I would still say this is more crucial than the scheduling itself. And still, if we also see that our kernel vectorizes well, that could be surprisingly slow, and that's what I will show you in a second, some reason why that could be. And just to remind you, the runtime commentary, so for the blocking, we saw that already yesterday enough. And then I also want to mention the coalescing, and I just want to jump to the examples for these two things. So for the vectorization, for example, could be that that the compiler could not vectorize because you maybe have some dependencies here in your loop, and in that case, you could easily help the compiler vectorizing by changing your code, like just removing these dependency here of variable I, and just replace it by the real loop counter itself, and then the code, the compiler could vectorize it. In, I would say, many cases, it's more or less simple, and even with the runtime commentary, the compiler tells you why it could not vectorize, so you can act on that. So if you really be sure that your loop has no dependencies and it should vectorize, but it does not vectorize, then you could also put the SIMD directive above the loop, and then really telling the compiler to do this vectorization. But you really should then check for correctness of this of your computation. And when you do that, remember, if you have any reduction clauses, you should repeat them with the SIMD directive. So with OpenACC, it's similar, but there you then should put the the ACC loop vector directive. And another point is, if you have a nested loop, maybe it's vectorizing, but it performs not well because the loop sizes are not efficient for in that case, the underlying hardware. So here, for example, if we have a really small inner loop here, which is maybe shorter than 32, I mean, shorter than a length of 32, let's say 8 or 10 or something, or maybe also 20, then we cannot perfectly map to one warp. So there's no nicely mapping to the SIMD operation, right? But maybe our outer loop is big enough to really fill the whole GPU with enough tasks, but it will not work out well since the inner loop is distributed over the SIMD direction. So what to do, and that we mentioned yesterday, I mean, one thing is that you can put the SIMD directive above the outer loop and parallelize that one. What you can do also in the OpenACC with the vector class. But the downside on that, since you then parallelize over the outer loop, so this is then here in the Fortran case, the second index, not the first index, so the slower going index, you have no contiguous memory access anymore. So to come around that, you have to work manually and then, for example, changing around index, so do kind of matrix transpose here, and then going in the first index with your parallelization. So this is just a short example here where you then can see, okay, you have these different problem sizes and you have the default behavior, and then you do this sequential operation of the inner loop, so you vectorize over the outer loop, and then in the second step you then additionally turn around your matrix index so that you act on the faster going index. But yeah, as mentioned, you really have to refactor your code, which means usually quite a lot of work, especially if you use these metrics a lot in your code in different places, right? So what else you can do? I mean, if your code already is vectorizing, but maybe it still performs badly, I mean, from a first point, I would still suggest profile and look where it takes the most time. And then be sure that you have a lot of parallel tasks you distribute on the code. And we already saw yesterday that profilers also present you this information. And then you can also think of maybe optimizing the partitioning to the different levels. And you mentioned that with the thread sizes, and in OpenMP we can also tune that so we can really adjust the numbers of threads per thread block and the numbers of we can adjust it by the numbers of threads block we want to use and also the numbers of threads within the thread block, and therefore we have the two clauses called thread limit, which has a certain value, so the default is here then 128 to set the numbers of threads per thread block, and the num teams values to set the certain amount of thread blocks. OpenACC, it's similar, and that's what you mentioned already. There we have the vector length and the num gangs, which is then which maps to the our behavior I showed in the OpenMP statement. So I already mentioned if you have these different sizes of also of the inner and outer loops. So for example, a really short inner loop but a really big outer loop, or also the other way around. You have a really big inner loop but a short outer loop. The total amount of of tasks you have within this loop cycle is quite huge to parallelize it over the GPU, but the setting from the default setting of the compiler is maybe not optimal to map that to the underlying hardware. So what you can do then is using the so-called collapse statements. I think most of you are aware about that, even from the host OpenMP parallelization. So you can then really specify the collapse 2 and collapse these two nested loops. So they have to be perfectly nested to one big loop, which then goes from for example, from index 1 to the product of the loop limits of the both inner loops, I mean of these both used loops. But the downside on that is that the compiler then has to find a mapping to all these loop variables, where he then has to calculate I and j back from the used ij loop index, right? And depending on your loop sizes, that could be quite inefficient. So yeah. So tuning these loop scheduling is really a tuning task. So you can really get some performance improvements with that, but in most times you really have to then change something on your code, so it's more harder work than just thinking about your data movement. I have here in the next slide a short case study, but due to the limited time, I would like to just skip that and then maybe also have some more time for more questions. So I would just jump over that. I mean, actually, it's just using the things I used before. So adapting the numbers of threads and the numbers of threads and blocks and collapsing loops and so on. And to conclude the first session, I just want to remind you that it's really, if you want to optimize your application, you should really first think about data movement, which usually brings the most speed up. Then really check if you cannot, or really check if you could maybe use already optimized libraries, and then really ensure that your loops really vectorize. I mean, that will also help your code in a pure CPU version. And then just consider maybe data reordering for helping vectorization and loop scheduling and collapsing and all this stuff. And then far, far, far later, if you really have too much time, then you could really consider much, much more advanced stuff like really hand coding CUDA. And yeah, my golden rules for performance tuning: really profile your code, optimize the real problem. So, I mean, we yesterday did with the Himeno benchmark really a short, I mean, a simple problem, but also with a small problem size, with a small matrix size. And we realized when we changed to bigger matrix sizes, also the problem changed. I mean, the behavior changed a bit. So really use also test cases for your application, which represents your real production then afterwards. And by profiling at the beginning, really concentrate yourself on the really important things, on these parts in your code, which really actually takes the most time. And then, yeah, keep on profiling to have an eye on that, and what is really crucial, I mean, actually yesterday we did everything right, so nobody ran in the issue that he produced wrong results, right? But I wouldn't say that this is the default case, so quite often we make mistakes, and then if we do not check the correctness of our code, we run in some issues much later, and then it's hard to debug it. And yeah, and the last thing, know when to start. So, I mean, the first steps maybe get a huge improvements, then optimizing more and more, you get maybe some more improvement, but it's getting smaller and smaller, and at a certain point you need maybe a lot of time to get 5% more improvement, and then you really have to think of, is it worth to do that? Therefore, I want to close this section and just want to show you the dependency stuff. Afterwards, you have questions for that? Was too fast?
So you showed how to specify how many threads will be in teams, gangs, and all these vectors.
Mm-hmm.
But in usual OMP, I can also say how it will be scheduled dynamically, or I want like 10 iterations being set to each thread and so on. So is it also possible here or not?
Excuse me, I did not get the question.
In the usual OMP, not the GPU OMP, I can write parallel loop for schedule dynamic,
Mm-hmm.
or say something about the scheduling, and I think it's a little bit different from what you were talking about, because there I think it sends like, let's say I can say I want 10 iterations to be sent to the thread. When it's done, it will come back and ask for another 10.
I mean, there's these tasks you can do in OpenMP. I don't know if you refer to that one. That's what I want to show in a second. But is it that what you mean? That you really create tasks and they
No,
work
not task
asynchronously?
creation. I just write one pragma parallel loop, or parallel for, or whatever it is.
Mm-hmm.
And then I say schedule, and I can say dynamic, or I can say schedule 50, and that will mean that 50 iterations will be given to a thread, and the thread will be doing them, and once done, it will come again for the next 50.
I mean, here you do it more indirectly. You really have your, let's say, loop counts or different tasks you want to do, and you specify how you want to distribute them with the amount of threads per thread block and so on.
Also remember our first discussion on the reduction, so it's different the way, I mean, on the CPUs, we usually partition the iteration space because we have very few cores or threads to use. So there it makes sense. I mean, you partition the iteration space either statically or dynamically. So there it makes sense to have this schedule, how you schedule those iterations. Whereas on the GPUs, we need, basically every iteration step, not iteration, I mean, in every element of your data structure of your array could be assigned to a single thread. So the parallelism is much, much higher, and it doesn't have, the scheduling is basically by default kind of dynamic because this is handled by the hardware. So it doesn't make sense from the GPU programming point of view to have such schedule dynamic or static. So that's why there's not something like that.
More questions?